Hello everyone and welcome to another episode of Interstigation. In today's episode of Interstigation, we will take a look at 2021 Fall AMC 10B number 11. A regular hexagon of side length 1 is inscribed in a circle. So here is a circle and there is a regular hexagon inscribed in it. I'll try my best to draw this, but it wouldn't be so regular. Well, states that each minor arc of the circle is reflected, Well, if we draw the center of the circle and connect it to each vertex, then that distance will be the same, right? Well, also, we know that the interior angle, or one interior angle, that is 120 degrees, because that's a hexagon, and that's a regular hexagon. And if you don't know that, you can divide it up into triangles. Let's say, the triangle, its interior angle is 180 degrees. If you divide it up like this, no angle is added. Or, of course, angles are added, but no degrees are added. Because, let's say, we have this angle, then this angle is split into 4 angles. But the sum of the degrees will be the same. Same with this, same with this, same with this. And we know that 4 of them, that is 4 times 180, we need to divide by 6 vertices. And since it is regular, each vertex will have the same number of degrees. So if we divide that out, we get 120 degrees. Therefore, if we erase these lines and connect them to the center, let's say the center is here, 1, 2, 3, 4, 5, 6, then each of these will be 60 degrees, which means that is actually an equilateral triangle. If the regular hexagon has a side length of 1, then the equilateral triangle all 3 sides of the equilateral triangle will have the side length 1, which means that the radius of the circle is equal to 1. In fact, for any hexagon, any regular hexagon that is inscribed in a circle, the radius will always be the same as the side length. Now, each minor arc of the circle can be determined by a side of the hexagon that is reflected over that side. So, if we reflect this side over this side, or this arc over this side, we get this. If we reflect that over that, we get this, this. Well, that is kind of hard to calculate because we have no idea how to do this curve unless you want to do integrals, which you probably shouldn't. It just wastes your time. On this problem, you could just calculate the area of the circle. So the area of the circle, that is equal to pi r squared, which is just pi because r is 1, and the area of a hexagon. Well, the area of a hexagon is just 6 of the equilateral triangles, and each of this, because this has 1/2, this will be root 3 over 2, which means that this area is 6 times this 1 times root 3 over 2 divided by 2. That's base times height over 2. That is equal to 3 over 2 square root of 3. Now, let's think about it. Well, this region outside of the hexagon but inside of the circle. How do we calculate this region? Well, this region, if you think about it, this region is just equal to the difference of this and this, because the entire hexagon is contained in the circle, which means that this region is equal to pi minus 3 over 2 root 3. That is all of these. Well, if we want to calculate the area enclosed by the red one, we need to subtract one of these again from the hexagon because these are reflected and these have equal areas. Therefore, we have pi minus this. This is the black region, and we need to subtract that from the hexagon. Therefore, we would have 2 times this minus pi, which gives us 3 root 3 minus pi, which is our answer choice B. Thank you for watching this episode of Investigation, and I will catch you in the next one where we discuss number 12. That will be an interesting problem to look at. Other than that, enjoy math and have a great day.